Hi class, let us begin week 2 by continuing in chapter 1, but now we're going to start with section 1.3. This is all going to be about points, lines, and planes. We have one objective in this section here, and all we want to do is learn the basic terms and postulates of geometry. Now what a postulate is just something that we assume to be true or take as a given. All right, so let's start with some undefined terms, okay? First, we have what's called a point. A point has no dimension, so it has no length, width, or height, so that's important to understand that a point has no dimension. But it does have a location or a position. So how we name it, we name a point by a single capital letter. Like for example, we have point A. We want to call it point A, we would say point A, or we would show a dot that would represent the point, and then the A above it would name it. All right, so we got a point. Now let's expand on this and talk about a line. So a line extends in opposite directions without end and has one dimension, length. It has no width, but it just has length. Now this is important to understand. A line goes on forever in each direction. It never stops, okay? So how we name it, right? We name a line with a single lowercase letter or by any 2 points on the line. Okay, any 2 points. Doesn't have to be point A and point B. Generally, that's what we'll use, but it can be any 2 points. So if this is our line here, you'll notice that this arrow and arrow, whenever you see that, that tells you it's going down forever and up forever. We have 2 arbitrary points, point A and point B, and then we can also call the letter or call the line this lowercase or italicized L. So we could say this is line L or line AB. So when you see an A and B next to each other with this line above it, that tells us it's a line. You can also call it line BA. All right, they're still the same thing. It doesn't matter what direction or which letter you put first. Still the same naming convention. All right, next we have what's called a plane. So a plane extends in 2 dimensions without end. All right, so the 2 dimensions are length and width. So remember, line just had length. Now a plane has length and width, but no thickness. Okay, so there's no depth to it. So we represent a plane by a flat surface. All right, so how we name it? All right, we name a plane by a single capital letter or by any 3 points on the plane. Okay, and this is important, that do not lie on the same line. Let me give you an example. All right, this plane here, this purple shaded part here, all right, we call that plane P. All right, now I know it looks like a rectangle, but remember that what a plane really does is it's going this way, down forever, and out this way, and out this way. All right, notice in there we have line AC, but we could also say this is plane A, B, C, and notice how those points A, B, and C do not fall on the same line. Important to know. All right, so let's do some examples. Write 2 other ways to name line. Now this is important. Line QT. All right. Well, we could just call it line M because we have the lowercase letter m here. Right? That's one way to name it. Right? Another way, excuse me, I gotta go back. Remember, we could call it QT, but we could also call it TQ. Right? So you could flip the letters TQ and call it, instead of calling it QT, you could call it TQ, or you could just call it line lowercase m. All right, so write 2 other ways to name plane P. All right, so plane P is this rectangular box here. Here's what's important. We have letters R, Q, S, and V. Right? Now all those points, those letters that represent points, fall on that plane. Now remember, you can't say plane RQS because those points all fall on a line. All right, but there's many ways to do this. 2 ways that we could name plane P are with R, Q, and V. R, Q, and V, those are 3 points that are not on a line, or R, S, and V. That's another one, 3 points not on a line. All right, so let's name 3 points that are collinear. Okay, so what this means is we got to name 3 points, right, that are all on the same line. Okay, that's what collinear means, all on the same line. So R, Q, and S are all in the same line, so they are collinear. Okay, next, let's name 4 points that are coplanar. So if collinear means they're on the same line, then obviously coplanar means that they're on the same plane. So 4 points that are on the same plane, looks like R, Q, S, and V are on the same plane. Not up here. T is not on this plane. All right, so points R, Q, S, and V lie on the same plane, so we call them coplanar. All right, next, let's name 3 points that are not coplanar. All right, so think about this. 3 points that are not coplanar. All right, there are many correct answers. For instance, the points T, Q, and V do not fall on the same line, so they are not collinear. Excuse me, I think I might have said coplanar. So they are not collinear. Another one that's not collinear. T, Q, and S are not collinear. V, Q, and S are not collinear, and so on. So things that do not fall on the same. All right, let's get another term. Space. All right, space is a set of all points in 3 dimensions. Right? So like we live in the 3-dimensional world, we live in space. So a geometric figure is any non-empty subset of space. So what that means is a geometric figure, it's not zero. It contains something related to 3 dimensions. So we use the term between when points are on the same line or line segment. Right, so for example, point B is between A and D, and also point B is between A and C, just like how we would think. Right? But notice here point B is not between A and C. So it makes sense that we use the term between, the same being on the same line segment. All right. A line segment, or simply segment, is part of a line. It consists of 2 endpoints and all the points between them. So the thing that's different between a line and a line segment, a line goes on forever, but a line segment is finite. So the way we name this, we name a segment by its endpoints, so A and B, or we call it segment AB or BA. And notice how there's a line above it that tells me it's some type of line, but it's a segment because it doesn't have the arrows that tells me it goes on forever. So for example, if we had the line segment here with A and B, we would call this line segment AB or line segment BA. All right, another one. Array is part of a line. It consists of an endpoint and all points in the line on one side of the end. So the way I also like to think about it is it has a starting point and it goes out forever. So how we name it? We name array by its endpoints and any other point on the array. Here the order of points is important. You list the endpoint first. So I can't stress that enough. You list the endpoint first. So when you see something like this, AB, all right, that means A is the endpoint, or if you want to think where it like emanates from, or we call it ray AB. So how you can visualize this? Here's your ray. The endpoint here, right, where the line ends, is A, and then it shoots on forever past that. So A, B with the line ray over. Another way you could do it, which is important, notice here the ray is going in the opposite direction. So its endpoint is B, and then it shoots off to the left, so we would say this is ray BA. All right, opposite rays are 2 rays that share the same endpoint and form a line. So how we name it? Name each opposite ray as you would name a ray. So for example, we have this line AB here. We have some point here C, right? Opposite rays would be CB that shoots out this way and CA that shoots out that way. Those are opposite rays. All right. So use the given figure to find the following. So let's do an example. So we got this line here, and we have the points on the line D, E, and F. All right. So name the segments in the figure. All right. The 3 segments are, we have DE or ED, that's one segment. EF or FE, that's another segment. And then the final segment, we did these 2 smaller segments, but there is a bigger segment, or DF, D to F, or F to D. Right. let's name the rays in the figure. All right, so remember, rays have an endpoint and then shoot out in a direction. So one here would be DE, which shoots out this way. Another one would be DF, that shoots out that way. Or you could have ED that shoots this way, or EF that shoots this way. Keeps going, look at this. You could have FD, which shoots this way, or FE that shoots this way, right? So think about this. Notice how there were 6 of them. That's pretty crazy. Which of the rays in part B are opposite rays? Well, think about this. If you have ray ED that shoots out this way, and EF that shoots out this way, when you combine them, they form a line with no overlap. So the ones that are opposite rays are ED, like I said, and EF. All right, so another example. Right, perform parts A through D in order to create a single figure. So watch this. I have these points. Okay, so let's draw 3 non-collinear points. So this means the points are not all on a straight line. So I'll name these points M, N, and L. All right, so the first one, let's draw a line MN. So all I'm going to do is draw a line straight through the points M and N. And notice how I have the arrows on the end that tell me it's a line. Now let's draw a line NL. So I'm going to take and draw a line right through here, or excuse me, this is draw a line segment, excuse me, because there's no rays here. No arrows on the end. Even I got a little ahead of myself. So I'm just going to draw a line segment from N to L, just like that. Next, let's draw the ray LM. So it's going to be the end point here, and it's going to shoot out past here, right, and go through point M. It's going to look just like that. So it looks like kind of what I've drawn there is a triangle of some type. All right, through any 2 points there exists one line. All right, so let's let L, this is our first postulate, by the way, right? 2 points determine a line. Through any 2 points there exactly one line. Line T here passes through points A and B. Line T is the only line that passes through both points. There's no other way you can draw a straight line that passes through 2 points. All right. When we have 2 or more geometric figures, their intersection is the set of points that the figures have in common. All right. So here's another postulate. If 2 distinct lines intersect, they intersect at exactly 1 point. So we have the line AB and the line BD, all right? They intersect exactly at 1 point C. Here's the thing though, they're distinct lines, they're different lines, they're not the same lines. Okay? If they're the 2 same lines, they intersect at an infinite point, but 2 distinct lines intersect at exactly 1 point. All right, so let's take a look here with an example. Name 2 pairs of opposite rays. Well, if you look here, at point here where they intersect X will be a point. If you go ray XM and ray XN, there would be opposite rays. And the same thing here, ray XP and ray XQ. All right, so the points M, N, and X are collinear, and X is between N and M. So XM or XN are opposite rays. And then the same thing that I showed you, points P, Q, and X are collinear, so X is between P and Q. So ray XP or ray XQ are opposite rays. All right, another postulate. Now we're talking about intersecting planes. So remember, intersecting lines form the point. So with planes, if 2 distinct planes intersect, they intersect and form exactly one line. So plane RST and plane WST intersect at the line ST, just like that. Let's do an example. Finding the intersection of 2 planes. Each surface of the box shown here represents a plane, right? What is the intersection of the plane ABC? So we have plane, ADC here, which is the top of the box, and plane BFG here. So it's the top and the side. Well, remember, 2 planes are going to intersect to form a line. So you have to figure out which line it's going to be. Well, if you look here, all right, shade plane ABC or ADC, the top, and plane BFG, see where they intersect. All right? Remember the postulate, they say to form a line. So where do they intersect? It looks like that part right there. So we can see that both planes contain points B and C, right? These define the distinct line. So they're going to intersect, just like I said, to form the line BC. All right, our final postulate, right? 3 non-collinear points determine a plane, just like I had defined, right? Through any 3 non-collinear points, there is exactly one plane. So there's only one plane that can go through all 3 points. So points Q, R, and S are non-collinear, then plane P is the only plane that can contain them. All right, so let's use this figure to answer the question. What plane contains the points N, P, and Q? And shade the plane. So here's N, here's P, here's Q in the corner. So if you think about that, the only plane that can contain it looks to be this bottom one right here. All right, so the plane on the bottom of the figure contains the points N,